This is my fifth video of Chapter 1 Real Numbers, 10th Standard Mathematics NCERT textbook. We were discussing the application of fundamental theorem of arithmetic. We have already discussed one application in previous videos, that is to prove irrationality of some numbers such as root 2, root 3, root 5, etc. And today we are going to discuss another application of fundamental theorem of arithmetic. That is to explore when exactly the decimal expansion of a rational number p by q not equal to 0, is terminating and when it is non-terminating or repeating. You already studied in your ninth standard that rational numbers have either a terminating decimal expansion or a non-terminating repeating decimal expansion. Or we can say there are only two types of rational numbers: terminating and non-terminating repeating. There are only two types of rational numbers. One is terminating and second one is non-terminating repeating. See example, what is 2 by 5? 2 by 5 can be written as 4 by 10, which is equal to 0.4. Here the decimal expansion terminates. And see what is 1 by 7? You just check it out. It will be 0.14287, again 14287, again it will be repeating. We can see this example in detail later. And here we are discussing when rational numbers have terminating decimal expansion and when it has a non-terminating repeating decimal expansion. Okay, revisiting rational numbers and their decimal expansion. In this section, we are discussing mainly three theorems and examples and exercises using that theorem. We can see the first theorem. Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p by q, where p and q are co-prime, and the prime factorization of q is of the form 2 raised to n into 5 raised to m, where n, m are non-negative integers. The theorem says that let x be a rational number whose decimal expansion terminates. For example, take 0.4. Here the decimal expansion terminates. Then x can be expressed in the form p by q, where p and q are co-prime. That is, HCF of p and q is equal to 1. Or the only common factor of p and q will be 1. And the prime factorization of q is of the form 2 raised to n into 5 raised to m, where n, m are non-negative integers. Non-negative integers means n, m can be 0 also. See, what is 0.4? We can write 0.4 simply 4 by 10. Now, this is 2 by 5. Here HCF of 2 and 5 is 1, or 2 and 5 are co-prime. Also, the denominator q has the prime factorization 2 raised to n into 5 raised to m, for n and m are non-negative integers. Here the decimal q is equal to 2 raised to 0 into 5 raised to 1. See, this is the theorem. We can see it in detail by exploring more examples and exercises. Hope you understand this theorem. Theorem is very simple. If a rational number has a decimal expansion that terminates, then it can be expressed in the form p by q, where p and q are co-prime, and The prime factorization of q is of the form 2 raised to n into 5 raised to m, where n and m are non-negative integers. Example. Consider the following rational numbers. First one 0.375, second one 0.104, third one 0.0875, and fourth one 23.3408. Here some rational numbers with a terminating decimal expansion is given. We have to write it in the form p by q, where p and q are co-prime and q has the prime factorization 2 raised to m into 5 raised to n, where m and n are non-negative integers. See first one 0.375. 0.375 is nothing but 375 by 1000. Or we can write this is equal to 375 by 10 cube. Here 375 and 1000 are not relatively prime or not co-prime. So see the factorization of 375. Here 5, 7, 5, 75, again 5, 15, 5, 3. So we can write 375 as 5 cube into 3 by what is 10? The factorization of 10 is 2 into 5. Therefore, 10 cube is equal to 2 cube into 5 cube. So we can write 2 cube into 5 cube. See, 5 cube is common here. Cancel it. Then we get 3 by 2 cube. Or 3 by 8. Here see, we expressed 0.375. 0.375 has a terminating decimal expansion in the form p by q, where p and q are co-prime. Here 3 and 8 are co-prime. The only common factor is 1. And the denominator or q has the prime factorization 2 raised to m n into 5 raised to m. Here 2 raised to n into 5 raised to m is 2 raised to 3 into 5 raised to 0. Here n is equal to 3, m is equal to 0. We can see next question. 0.104. 0.104 is nothing but 104 divided by 1000, which is 104 divided by 10 cube. Now see the prime factorization of 104. 104 is 2, 52, again 2, 26, again 2, 13. So 104 can be expressed as 2 cube into 13 by 10 cube is 2 cube into 5 cube. Here 2 cube get cancelled, which is 13 by 5 cube or 13 by 125. The denominator is a 5 cube in the form 2 raised to m into 5 raised to n, with m is equal to 0 and n is equal to 3. Here see, you may notice the way we are proceeding. Here we are expressing it in denominator in the powers of 10, and powers of 10 have only powers of 2 and powers of 5 as factors. Next one 0.0875. 0.0875 is nothing but 875 by 10,000 or 875 by 10 raised to 4. Here see the factorization of 875. 875 is 5, 1, 7, 5, again 5, and this is 3, 5, 5, 7, which is equal to 875 is 5 raised to 3 into 7, and 10 is 2 into 5. Therefore 10 raised to 4 is 2 raised to 4 into 5 raised to 4. 2 raised to 4 into 5 raised to 4. Therefore 5 raised to 3, 5 raised to 3 get cancelled. Here remaining 5. 7 by 2 raised to 4 into 5. Similarly, fourth one, 23.3408, which is equal to 23.3408 by, here after the decimal 4 numbers, therefore 10 raised to 4 or 10,000, which is equal to, we will get it as 2 square into 7 into 521 by 5 raised to 4. So that is the first theorem. Any rational number with a terminating decimal expansion can be expressed in the form p by q, with p and q are co-prime, and q is of the form 2 raised to n into 5 raised to m, where n and m are non-negative integers. Or we can say that denominator is powers of 2 or powers of 5 or powers of both. Next theorem. Let x is equal to p by q be a rational number such that the prime factorization of q is of the form 2 raised to n into 5 raised to m, where n m are non-negative integers. Then x has a decimal expansion which it terminates. Theorem says that if x is equal to p by q is a rational number with the denominator or q is of the form 2 raised to n into 5 raised to m, where n and m are non-negative integers, then this number has a terminating decimal expansion. This is just the reverse of the theorem 1. Theorem 1 says that if it have a terminating decimal expansion, then it can be written in the form p by q, where q is 2 raised to n into 5 raised to m. And this theorem says that if it can be written in the form p by q with a q 2 raised to n into 5 raised to m, then it has a terminating decimal expansion. We can see example. First one, 3 by 8. See, 3 by 8 is equal to 3 by 8 is 2 cube. 2 cube. Now we can multiply it by 5 cube to get 3 into 5 cube divided by 2 cube into 5 cube, which is equal to 5 cube is 125. 125 into 3 is 375 by 2 cube into 5 cube is 2 into 5 the whole cube, or 10 the whole cube, or 1000, 10 cube, which is equal to 0.375, a terminating decimal expansion. Here you may note that we are converting the rational number of the form p by q, where q is of the form 2 raised to n into 5 raised to m, to an equivalent rational number of the form a by b, where b is of power of 10. Here this is a rational number with q is of the form 2 raised to n into 5 raised to m. We are converting it into the rational number of the form a by b, where b is power of 10. Clearly we know that any rational number of the form a by b, where b is of power of 10, will have a terminating decimal expansion. That is the concept we are using here. Okay, we can see another example. Second one, 13 by 125. See, 13 by 125 is 5 cube. Now we have to make this denominator power of 10. To make it power of 10, we can multiply the numerator and denominator by 2 cube. This is 13 into 2 cube by 5 cube into 2 cube. This is nothing but 8 into 13 is 104 by 5 into 2 the whole cube, or 10 cube, which is equal to 0.104. Next example, 7 by 80, which is equal to 7 by, the prime factorization of 80 is 2, 40, again 2, 20, 2, 10, 2, 5. 80 is 2 raised to 4 into 5. Now to make it a power of 10, multiply the numerator and denominator by 5 cube. Then we get 7 into 5 cube by 2 raised to 4 into 5 raised to 4, which is 10 raised to 4. Now 5 cube into 7 is 125 into 7, which is equal to 875 by 10 raised to 4, which is equal to 0.0875 after the decimal 4 numbers. And this is the second theorem. Any rational number of the form p by q with q is of the form 2 raised to n into 5 raised to m has a decimal expansion that terminates. Here we are using the concept that we are converting this rational number to a rational number of the form a by b with the denominator is power of 10. Now we can go to the third theorem. Third theorem. Let x is equal to p by q, where p and q are coprimes, be a rational number such that the prime factorization of q is not of the form 2 raised to n into 5 raised to m, where n, m are non-negative integers. Then x has a decimal expansion which is not terminating, repeating, or recurring. The last theorem was that if a rational number with the denominator 2 raised to n into 5 raised to m form, then it has a terminating decimal expansion. And this theorem says that if a rational number with its denominator is not of the form 2 raised to n into 5 raised to m, then it has a non-terminating, repeating decimal expansion. Example 1 by 7. See, the denominator is not of the form 2 raised to n into 5 raised to m. You can see the decimal expansion of 1 by 7. 1 by 7 is 1 divided by 7. Here 0.10. Here 1, 7, 3, 30, 4, 28, 20, 2, 14, 60, 8, 56, 40, 5, 35, 5, 7, 49. Again this process will repeat. Here 10, this is 1, again 30, 28, like that it will repeat. Therefore 1 by 7 is 0.142857, again 1428557, and it will not terminate, not terminating, and it is repeating. From the above theorems, we can conclude that the decimal expansion of every rational number is either terminating or non-terminating, repeating.